Hi, and welcome to part 2 of Lecture 8. In this part, we're going to talk about how we fit the distribution and how we evaluate the fit that we did. So first, we need to know, we need an example. So we're going to load up the arrival times that were collected for the Nimex coffee bar. So here we can use a handy function, read Excel. It's in the read Excel library. You have to make sure that package is loaded, of course. And then it's just one simple command in R. You have to give it the name of the file and the range and the file where the data is. So it's a pretty handy function because there's not much more you need to do than have an Excel file with it. We're going to load something called dplyr. This is going to allow us to manipulate the data so that we can convert it from arrival to inter-arrival times. Okay, and we do it after we load it using the library command again. This is all warning stuff. We use this kind of complicated command here where basically we're going to replace the data we have. We're going to say, okay, where the source for it is arrival data, so it's the sources itself. We use this connector % greater than % that connects different commands that we're going to use. We're going to arrange the times and we're going to mutate them. So we mutate them so that we compute the inter-arrival time here actually. Okay, so we say the inter-arrival time is arrival.time minus what is called the lag of the arrival.time, which is the consecutive time before it. Okay, so we've sorted it. And then we're going to mutate it further. We're going to say, look, if that is less than or equal to 0, then make it 1. Otherwise, use the inter-arrival time. Okay, so we're going to round up every inter-arrival time. We're going to round up to the nearest to ones to make it at least 1 second. So this is something we have to be a little bit careful of because note that this is not what we need to do a different thing if we have, say, groups of data like you have in your barbecue. Okay, so we need to be careful about the assumptions. Okay. So I'm going to talk about later in class about how to handle like the data you might have in your barbecue pit. Okay, because this assumption makes there's at least 1 second between different arrival observations. Okay, so that worked for our cafe data, and now we can plot a histogram. So this is going to be a good way of establishing, histograms are going to be useful for establishing what candidate distributions you might want. Okay, so the key part of doing a good histogram is determining the right number of bins. Okay, so for this we're going to use ggplot. Note how ggplot uses basically something very similar. It uses a connector syntax, but here the connector syntax is plus. So ggplot needs a data set. Here it's arrival.data. And then we put in different commands in order to turn it into a histogram. geom_histogram says a histogram. The x is going to be the inter-arrival time. And then this is just, we just chose arbitrarily 12 bins, and this is what it looks like. So when you look at this, I hope you would think this is exponential, but you might be thinking, well, why 12 bins? And I think that's a really good question. And in fact, there is a better way of choosing the number of bins. It uses what's called the Friedman-Diaconis method, and it says the number of bins should be equal to 2 times q divided by n to the cube root. Q is the difference between the 75th and 25th percentile, and you might think, oh geez, do I have to remember this whole formula? It's good to know it, or it looks good to know that you can look it up, but of course in R, we're lucky in that we have a function that's going to calculate this for us. So we can calculate the number of bins from that and then compute that using this Friedman-Diaconis as follows. So we have the R code there in that block. And it gives us this different looking, this I think the exponential or gamma shape becomes clear. Okay, so now these are going to be our 2 candidates, either exponential or gamma, and then the question is how do we go ahead and fit that? So what we're going to use to fit it is we need to calculate out the parameters for each of these distributions. So we need to find either the mean of the exponential, that seems relatively easy to calculate, so we can get the rate, or we need to get the shape alpha and rate beta. So how do we calculate that is we're going to use the standard method, which is maximum likelihood estimation, and that is computed for us within fit_dist r plus. And what it's doing is it's finding out, it basically calculates this likelihood function, and it figures out the parameters that maximize this likelihood function. So it's actually solving an optimization problem to figure this out. And it's good that we have that function because that will do it for us. And let's see how that code looks. We have to, again, load the library. So make sure you have installed that package, and then you can use this library command. Remember, the install package is in that menu item, so you have to make sure that's there. Then you can use the library command. Then the code block that does it here is actually this. The first line there is computing a new data set. It's going to have the old data set in it, plus it's going to have the fit. And here the fit is exponential, as denoted by that argument, quote, exp. And then we have the summary. So it gives us the summary, and it gives us here the rate parameter for the exponential. Then we do the same thing, and we find the gamma. Right, again, the quote gamma is what says to try to fit a gamma distribution, and it gives us the shape and rate here. I'll tell you what these scores mean in a second, the log likelihood and the AIC, BIC. Okay, so to summarize, the fit_dist found an exponential distribution with a rate parameter given by the 0.024130019, and the gamma with the shape 0.6, so on and so forth, and rate 0.01448016. Okay, so which one do we use? Okay, we have to evaluate this fit. And we can look at it visually. And we can also use a goodness of fit criteria. And then we have another criteria called the Kolmogorov-Smirnov statistic. So visual inspection, we can use this function dense_comp. It will actually let us look at different fits like this. And it we have to give it what each fit is by giving us that label. Remember, C creates a column in R. And then the plot style, we use something called ggplot. Okay, and it automatically plots the things for us when we put in that command. When we look at this data, the visual evidence does not support one fit over the other. Okay, so we could even say that this visual was inconclusive. They both seem to work. It provides evidence that both fits are good fits. Okay, so then we can turn to something else called a goodness of fit criteria. The AIC and the BIC are the two we'll focus on here. Here, the important thing here is K is the number of estimated parameters. Remember, I've talked about complexity, and K is our measure of that. K equals 1 for exponential, and K equals 2 for gamma. Remember, that's because the exponential requires a rate, and a gamma requires a shape as well as a rate. Okay. So the alpha and beta for gamma, and then the mean or the rate for the exponential. Okay, the lowest AIC or BIC is preferred, and that's going to be true for all the scores that we look at. We're actually going to see a bunch of scores given by the tests we run, and we always want the lowest number. Okay, so as the L here, L hat, is the likelihood. You can see that as that likelihood increases, AIC and BIC both increase because we're subtracting out the log of that. And then as K, the number of parameters increase, both AIC and BIC increase. That's reflecting the importance of complexity. And that in BIC, that's actually increased even more by the number of observations. So the more observations you have, it's penalizing complexity even more. So we can use GOF stat from our fit dist r plus library to calculate this. Okay. When we do so, this is the, we grab the GOF stat into this thing called interarrival.gof, and it prints out. And you can see here that in all cases, the lower statistics, that for the AIC and BIC, the exponential is higher than the gamma. These scores also, I haven't talked to you about what they are, but you still want lower. But in any event, what we can say is the AIC and BIC. So here is evidence gamma is a better fit. Because it was lower than the exponential. Okay, the final test we'll talk about is the Kolmogorov-Smirnov statistic. The first thing we need to think about is the empirical CDF. What this is it's a way of constructing from data cumulative distribution function. So this is, and if you think about what that means, is over all the observations for a given A, how many of them are in fact less than or equal to A. So that's represented here or described here. And so you can think if you were just given a bunch of data, you could actually construct this cumulative distribution function. Okay. So in R, of course, we have a command that computes that for us. It's called CDF comp, and it's going to compare these different fits with this empirical CDF. And it gives us something that looks like that. And with the Kolmogorov-Smirnov, we want to get the maximum difference between the empirical CDF and the theoretical one. So what is that? The black line, you can see it's a step function for the CDF because that jumps for each observation with a different value that's higher. For the green line here is our gamma, and I guess this black, the vertical difference is highest maybe right here. Or, yeah, it's hard to say, but perhaps in this region, it looks like it might be highest. The difference between the black empirical and the red might be highest right around here. In any event, I don't need to. We can visually inspect it and look, but of course that's imprecise. Instead, what we can do is we can just print from the GOF our KS test, and we can see that if we print that, it is going to tell us if it was rejected at 0.05. What does that mean to be rejected? The null hypothesis is that it did come from the distribution. So if it's rejected, that's evidence that this wasn't a good fit. If it was accepted, then it's evidence that it was a good fit. It's rejected in both cases. So because we're trying to figure out which of these two best fits it, we could say that the KS tests did not provide evidence that favored gamma or exponential. Okay. So I'm going to stop there. I'm going to say that if we were writing up this report or we're trying to choose a distribution, we would probably choose gamma here because of the AIC and BIC evidence. The visualization, the histogram didn't really favor either distribution. The KS didn't favor either distribution, so we will go with, so there's only one thing that did provide evidence of one over the other, and that was the AIC and BIC. The other two tests that we looked at didn't really favor one or the other, so I would say that this supports using a gamma. You can start to see how this really is an art. I could see somebody making some argument that even the AIC BIC was not a very strong, it wasn't strongly favored, so we're still going to go with a less complex distribution. And again, that's going to be a matter of experience, context, and some amount of subjectivity even.